Oh, thank you. That's great. Hello. We're delighted to have Xiaoliang from Stanford. Xiaoliang work spans condensed matter, high energy theory, and machine learning, and also maybe afterwards and he's going to give us a talk about a phase diagram for deep random transformers. And also Xiaoliang has a side project around LLMs in the archive that you might want to ask him about after the talk, unrelated to the talk, but might be of interest. And yeah, take it away.
Thanks, Dan, very much for the invitation and introduction. I'm a newcomer in the research of machine learning, although I did some works before which try to relate the procedure of learning to the description of quantum information by space-time. That's also the area of quantum information and quantum gravity. That's also an area that Dan and I collaborated long ago, and really, it seems like we are both moving to the machine learning direction. And so today's talk is about some phase diagram, some way to analyze transformer models more systematically and attempt to do that for initialized, for the initial model. Sorry, why is it not? Okay. So this is a work mainly led by these two outstanding graduate students, Aditya Kaushik and Tamara Nevabu, and also in collaboration with Sriya Ganguly, a colleague of mine at Stanford, and probably many of you know his really significant works in machine learning. So especially Aditya is really the leader of this work. If there's questions I can't answer, I'm sure he can help me. He's online. Yeah. And this work is in progress. So we haven't finished writing. Hopefully it will come out soon. Can you hear me well? Okay, thanks. Yeah, so the main goal is there a laser pointer? Never mind, yeah. The main, sorry. Oh, okay, thanks. The main goal is to understand the phase diagram of transformer at initialization. So it means, I mean, of course, the trained transformer, like the large language models, can be very rich, and it will be very hard to have like a systematic phase diagram. We are looking at the behavior of transformers at initialization, which means we take some random initial conditions, and then there are hyperparameters in these initial conditions, and we want to understand the behavior in terms of these hyperparameters, which means it's a phase diagram. And then, so we want to, based on, so this is like a generalization of the models for a generalization of similar discussions for other kind of machine learning models to transformers, where we want to have criteria for good initialization, and we will have some analytical results and numerical results on this phase diagram, comparing with different approaches with each other. And then in the end, I will discuss some conclusion and open questions. Please feel free to interrupt me anytime if you have a question. So probably many of you are familiar with transformers, but just in case, and also just to recap for myself, I want to be very concrete and then start with what we are studying. we're studying this transformer model, and then we are looking at the deep limit. So we're like taking these many layers of transformers, and each layer of transformer contains two parts. There's attention, and then there is the feed-forward neural network, the multi-layer perception. And then in each layer, what you do is there is a residue. So what you do is you take this input and then go through the normalizing it, and then apply this attention mechanism. And then after that, you give it a weighted superposition with the original vector, and then you get the output, and then you do a similar thing for the MLP layer, and then you get the output for that next layer. And then so the attention and the MLP, these two main building blocks, I mean, I think this is totally unnecessary, but for me, I like tensor networks, so I want to draw it in the form of tensor network. So I don't think people have, and this probably doesn't look like a standard thing in machine learning. But but if you think about what happened to the attention, it applies to a bunch of vectors, right? So every token is a vector. So in other words, it applies to a matrix. And the matrix has two labels, the internal dimension A and the token label I. So then when you do the attention, what happened is this token label I, or J here, the token label J here got multiplied by this attention matrix A, IJ, which is this matrix. So that doesn't apply to the internal dimension. That applies to the token dimension. And that matrix itself is determined by this input in this diagram, which means I took this matrix and then take an inner product. After applying it to the Q and K matrices, I take an inner product between them in the internal dimension, and then I'm left with the IJ labels of the token, of the token label. Right? So say if you have n, let's say this internal dimension, let's say is D, and then the token label is L, then you get this L by L matrix, and then you apply the softmax, which makes it some nonlinear, which is just a nonlinear function of the inner product, and then nonlinear function translates the closer vectors, so the closer bilinear form, like the bigger value of the inner product to a bigger attention, to a bigger probability of relating them, and then you take this weighted sum. So that's basically what this diagram means. So the bottom line is that it's a nonlinear function. The output is a nonlinear function of the input matrix with the same size. And then the MLP layer is simpler because it applies to every token separately. So for each input I, then you'll just apply to the internal dimension A by first take a superposition between them, and then apply this nonlinear function, which could be a real U or could be a tangent, parabolic tangent, or some nonlinear function, and then you apply another linear transformation. So that's still not like the most general architecture you're using in reality models, because you have like multi-head and so on, right? So this is like other than these, this is relatively complete structure of the model. Any questions so far? Okay, good. Yeah, so intuitively, now this is not a tensor network picture, but a more intuitive picture. Intuitively, what this transformer model is doing is like I have these input vectors, and then they have some relation between them described by the attention matrix. And then the thing that has more attention with each other will influence each other more, and that's done by this interaction. It's like interaction between these vectors only happens here. And then there is the MLP layer, which is not interaction. It's like a single particle term. It's like on every vector separately, you squeeze them in some way, and then you go to the next step. So it's like attention is doing a job of mixing different things non-locally, and then there is a local nonlinear transformation that gets you prepared for the further processing. So, okay, so then now if we look at more details, if we look at these equations I wrote in the previous slides, so you have like the attention layer involves Q, K, V matrices, And then the MLP layer involves these two matrices W's. So these are the parameters you have. Sorry, these are the parameters you have in this model. And these parameters, there's a lot of them. So there's like if I'm talking about initialization, so these parameters are chosen to be random parameters. And then for simplicity, we will choose them to be independent random parameters. So basically, all the matrix elements of these matrices are independent random variables. So they are described by width of them. And so in the MLP, there are two width of the two matrices. And then there is QKV. Each of them has some width. And then there is the alpha parameters, which determines how much residue you want from the previous layer. So then, because we assume these are all random, so to make sure the norm is more or less the same in each layer, because you don't want it to be just trivially like becoming bigger or becoming smaller. So you will choose like the alpha tilt to be this form, because on average it's like here, like on average these two parts are more or less orthogonal to each other. So you choose square of this and that to be sum equal to 1, so that it's on average it's preserving the norm. Yeah, so basically to simplify the problem, we are discussing some we are choosing some we're choosing some way to reduce the number of parameters. So sigma W2 can also be absorbed because when we think about the random ensembles, then like if you rescale sigma W2 to the leading order, it's just changing how much, like if you rescale this W2 here, it's going to just change the amplitude of this whole thing. And then, but after that, you have this norm. So you can also just choose the sigma W2 to be always 1, and then just redefine the alpha 2. That's I don't think that's exactly true, but if you only care about the amplitude, then you can choose the W2 to be sigma W2 to be 1. And then similarly, the sigma V can be absorbed to alpha 1. So we will choose that to be 1 also. So then the thing left is like the width of the random variables for Q and K. And then because Q and K always multiply to each other, so you can look at their variation. You can look at the product of their variation. So of course, in terms of random ensembles, this is different. And so like a random ensemble Q and K, when you multiply Q dagger K, it's not an independent random variable anymore. But to the leading order, so numerically we see they are not very different. So like when we do the later when we talk about the more analytical calculation, we were actually assuming Q dagger K as a random matrix. But numerically, you see it's not much different from just separately choosing Q and K to be random. So higher correlations may be different. So in summary, the key variables left are the alpha 1, alpha 2, sigma W1, which is like the random variable you feed into the nonlinear function in the MLP, and sigma A. Right? So these are the 4 parameters that will be the hyperparameters we discussed in this work. Any question? Yeah.
You haven't talked about.
Oh.
You haven't talked about the very beginning where you go from the vocabulary or tokens to the embeddings, and then the very end. In principle, there's random variables there at the beginning of training, and you have to choose their widths as well. Is that something that you consider?
Yeah, we haven't studied that because the way we want to look at the phase diagram is like in a deep limit, how much, like if you apply this kind of random transformers many steps, what will happen? And then basically physically, you want to avoid 2 situations. One is like whatever you input, you get the same thing after several layers. So it's kind of the initial condition is trivial, has no influence. And the opposite limit is like it's too sensitive to the initial condition, so it's kind of chaotic. So we want to be somewhere in between. That's like the general criteria. So I think for that, the initial, I mean the first layer doesn't matter for that. But yeah, but maybe if we restrict the finite depth of layers, then this matters.
Yeah, you could also imagine repeating, or I guess a single layer could still be, if you repeated it a lot, could behave poorly. And so you might think that even just one application of a bad choice could be bad.
You mean if every layer is like the same?
Well, yeah,
yeah. So here is like every layer has some the same ensemble parameters but different realization. It's like Brownian situation. So then the initial condition probably doesn't matter so much. Yeah, I think you're right. If I have exactly the same parameters in each layer, and I apply that many times, then I think the initial condition will matter more. And I don't know if I would still expect like generically the initial condition, like most of the initial conditions are the same, but maybe there's some fine-tuned ones which will be different. Is that the case? Okay. Okay, so then we start by some intuition, which is that that attention basically means that the things that closer to you will have a bigger effect, bigger influence to you. Right? So the vector that are like you think these vectors as points on the sphere, and then the points that are far away from you will have less influence. So it's kind of like a gravity. Right? It's like a so that's why you see this videos. This is videos for pure attention. This is like if you just have pure attention, like you just apply the attention mechanism many times, then the T is like how many times you apply that. So you see it's kind of like the structure formation in our universe, right? Like you start with some random initial points, but then they start to concentrate because things closer to each other like to get even closer. But then that's maybe to some extent that's a good thing because you kind of learn clustering, right? You learn how like things at different parts are belongs to different classes maybe. But we are interested in this limit of applying this many times. So this is mostly a problem because it will just collapse everything in the end to like the same point or the same several points. And these two figures are different because the one on the left is like with the trivial embedding matrices, and then like Q and K are trivial, and then the one on the right is like Brownian. So you see a little different, like the thing on the right looks a little different, but they both will collapse in the end. So then that's okay. So the intuition is that we want some neural network that will represent some very complicated data. So you want like all the important information in your data, like when you train this model, to go into this model, right? So you don't want a model that's like saturate easily and doesn't learn anymore, right? So after some layers, right? So if you want the depth to be useful, then the intuition, which is following earlier works, including this important work of Surya Ganguly and collaborators in 2016, where they did this discussion for the feed-forward kind of neural networks. So it's so the situation you want to have is when first you want the initial condition to matter, right? So you don't want like whatever input vector you have, they all converge. Then that's not so useful. You want them to you want them to avoid this rank collapse that you see in the previous slide. Like you want these vectors to have a non-trivial dynamics even after many layers. So it's kind of they move in some non-trivial way. They don't just converge to one point, and they also don't get like divergent arbitrarily. Right? You don't want a situation where it's chaotic. So when you change the initial condition a little bit, things change dramatically. In which case, like you really just couldn't control the output, right? You really couldn't train based on the output. So you want a situation that's between, like at the critical point between two things. One thing is that the angle, right? The angle between the input vector, right? So you can look at how the angle evolves, and we assume so on average every layer is the same, but there are different parameters. But if you talk about average, on average, how big is the angle? Then either they become smaller and smaller, or they become bigger and bigger. So that's the evolution of the angle. And then there's the other condition, which is like you want this gradient to be not vanishing, which means like you want the output to like not only they have some angle between each other, but also like they depends on the input, right? So like when you change the input, how does the output change? Right? You don't want them to be like all frozen to one direction. So these are two different criteria. We call them forward and backward because when you go forward direction, you see how the angle evolves, and when you take derivatives, you see the gradient which propagates backwards. And then so you want both of them to be at the border, means that they almost remain the same amplitude in layers. So there are two criteria. One is the angle theta n plus 1 is almost equal to theta n, which means Cij, like the inner product between vectors, if you compare it with the diagonal, the ratio cosine theta like almost remains the same. And the other criteria is like the gradient will be around 1, like the determinant of the gradient be around 1. So which means we can define two things we call the Lyapunov exponent. Like usually, yeah, so it's like you imagine they are like the chaotic systems, then this Lyapunov exponent should be close to 0. That's your requirement. Although this is not really a Lyapunov exponent because it's like a Brownian system. Right? Okay. Any questions? Okay, so yeah, so that's basically the criteria we want to apply, and then the question is how do we study this? How do we really compute these quantities? And so what we are going to do is we have some way to analytically, like under certain approximation, analytically study the evolution of this angle. And then for the gradient, we will rely on the numerics. So let's analyze the symmetry of this ansatz. Right? So we choose these matrices to be random. So you start with some input token vectors, and then you just apply random transformations. So on average, when you average over the ensemble, there is an SOD rotation symmetry for the internal dimension D. Right? So the internal dimension can be rotated by these matrices, and then after you average over what transformations you carry, then it's like rotation invariant. So also there is a permutation symmetry between the different tokens. So we haven't introduced things like position embedding, and so it's a permutation invariant. So so considering these two symmetries, it's natural to write down an ansatz because we're interested in these angles between different tokens. So it's natural to write down an ansatz that's a permutation invariant, which looks like this, right? Like the inner product between different token vectors. The diagonal one is like the norm of the token vector itself. And then the off diagonal is like between two different vectors. And then because of permutation symmetry, the average is the same for any pair. So really there are two parameters if you assume the permutation symmetry is preserved. There are two parameters, the diagonal and off diagonal. But this is not saying the permutation symmetry requires you to have this. Right? So it's possible to have kind of spontaneously chosen, like you choose some initial conditions, and then you get this situation where the inner products are different. Right? So it's like think about this clustering picture. When you have this vector on the sphere, you could have like one cluster that goes here, the other cluster goes there, and then the inner product between them has a different behavior from within each cluster. And so we will discuss a little bit of this more complicated situation. But the short message is that if you start with, it seems this is a stable situation. Like if you start from start from something that breaks permutation symmetry, at least locally, when you break it a little bit, it will come back to this permutation invariant ansatz. In the sense of random averaging. So then assuming that you have this permutation symmetry, then when you apply this transformer layer, the symmetry will be preserved on average because of the symmetry, because after you're averaging over the ensembles, permutation symmetry preserved. So you will get an iteration equation of these two parameters. So you put in an ensemble where so the ratio between P and Q will be the parameter that tells you the angle, right? So then the angle next step will be given by just repeating these two iterations. So you have an input vector, and then you first put it here. So you get this complicated thing coming from the attention, and then you get this coming from the MLP. And so you just convolute these two functions, and then you get convolve these two functions, and you get this iteration equation. So there's some approximations here. I didn't write on the slide. So yeah. So when we do the averaging, we were taking some approximation, because what you need to do is you need to take this kind of matrix, and then there's a bilinear of them, right? You need to take two A's and then average over that, and then in general there will be more terms. So we were taking the averaging over the top of the numerator and denominator separately, and that's an approximation, which numerics seems to confirm that's a good approximation. We hope to have a better analytical result, maybe based on replica and other things in future. Yeah, you have some.
I was just going to ask if it's a large D thing, but you said the replica thing makes sense too.
I think well, certainly we need some large D in term. I believe in larger D it will work better and better. And we don't have a very big D. There's a D here. So yeah, D is 64, and that's already working pretty well. Yeah. Yeah. Okay. So this is the numerics for the iteration equation. So so you have so all the numerics are for D equals 64, and then the number of tokens is like 256, and then so we have this activation function, which we choose to be the tangent function. I can explain a little bit later why that's what we studied. Okay, so you choose the tangent function and then run this iteration. So you start from somewhere. We started from somewhere here, which is like you assume the vectors on average are orthogonal with each other. So they have norm 1 and norm D actually, and then they are orthogonal with each other on average. And then you see that they will, because of the attention, they will start to get closer to each other. It will build this this non-trivial overlap, and then eventually there are two possibilities. So in some region of the phase diagram, you will converge to T equal to Q. It means this is 1. So you will basically collapse into the same vector. And then there is the other region where that's unstable. Like if you start from somewhere close to there, it's going to move away, and there is a fixed point somewhere else. So there are these two different phases, and then our criteria will be we want to be at the phase boundary between these two. Yeah.
Sorry, just one other question. I guess does the limits relative ratios of D and L matter?
That's a good question. Yeah, physically, it certainly matters, because if L is small and D is large, I can really make these vectors orthogonal with each other. And then I think in our calculation, we but I think this, like this approximations we are taking here, I don't think they assumed whether D and which one is bigger. Like the question is whether these two limits commute. So I have the impression that they commute, but I'm not sure. Aditya, do you have a comment?
I think that this D over L ratio in like this setting is not the most important thing, because what D controls is the fluctuation of basically the individual terms. Or actually, sorry, D doesn't even control the fluctuation of the individual terms. It's just that, like, if N is much, much, much larger than D, then you really can't pack vectors into the D sphere very far away from each other, but that happens when they're very far apart. So it's not clear to me that the interaction between them is like too strong. Don't know if that's, I don't have like a great idea about it, but this is my intuition.
we start from somewhere close to P over Q equal to 1, that's like if you have random vectors and a lot of like L is very big, then probably they all are kind of close to each other. So you will be starting from here rather than here. But the fixed point will be the same.
I guess physically, well, I was originally going to say maybe this is not the physical or not the limit that the at least previous LLMs that are published on are work in, but I guess this is per head. Like this is, I should think of this as like a single, it's not multi-headed.
Per head, yes.
And so then the local dimension actually does kind of make sense. So I retract the question.
Oh, so then you say it makes sense that the ratio doesn't matter?
No, well, I was going to suggest maybe it was the ratio is reversed in the physical regime, but actually if it's per head, I think this is more reasonable.
Yes, because every head is smaller. Yeah. Right.
Thanks.
Okay, so then, for example, this is a comparison of what we get from the iteration equation and the numerics. So just to clarify this, what this picture means is like the behavior near the fixed point. Like if you, I mean, this iteration, we started from far away from that point, but the plot next slide is like if you start near the 1, 1 point, like near when P and Q are the same, which means you start from two vectors that are very close to each other, then do they get far away or do they get closer? So the red region is when you have a positively up node, like you diverge. And then the blue region is when it converge. So the white part is like the critical point. And then this part is all white because like when alpha is very small, the whole thing is like close to trivial. Right? So on the diagram, you always see like this part is like very close to trivial, but then there is this phase condition, the phase boundary. And then this part, the diagram on the right is confirming that actually this approximation works pretty well because like this is for actual like random QKW matrices, like without doing the averaging thing, you really have this actual random QKW, and then you can run that and then compute how does the average angle evolve in from one layer to the next, and then confirm that this averaging we did is a good approximation. And then this is this is showing the effect. Sorry, the effect of the of how it's basically like the temperature. Right? It's showing how the attention sigma A, like the fluctuation of Q dagger K, how does that change the analysis? And it turns out to be not so important here. So it's like the attention is, because it's so random, so it's like just mixing different things. So even if Q dagger K is very, like whether it's bigger or smaller, it's doing the same kind of like random averaging. So it doesn't really change much. So yeah, so this is, but the important thing is to take a look at this together with this picture. So say this picture is like the first criteria, like how the angle changes with layer, and then we want to be near this critical point. But then there is the other condition, which is the gradient needs to be near 1. So this is the white part here is like the log of the determinant of the gradient. So it's like the phase boundary here is different from the other criteria. So if you want to satisfy both criteria, it will be somewhere here. And this is just for a different sigma A. So if you look at this one, which is the same parameter as the previous slide, then if you put two of them together, then it's like this picture. So here, this is just a way to plot the data. This is plotting like the norm sum of the two Lyapunov exponents. So you want both of them to be very small, so you want to be in the yellow region. So like the small alpha is like close to trivial, so everywhere is close to 0. But this part is like the non-trivial sweet spot. It's like here, you have both criteria satisfied. But then if you go away, like this part is where one criteria is satisfied, not the other. And this part is like, like the gradient will be close to 0 here. The gradient of Lyapunov and then the angle of the optimal will be close to 0 there. So there is the intersection around here. And then you can show, this is just the same data shown in a different parameter range, because I forgot to say, but previously I'm taking the alpha for the residual value, right? The alpha, this is like 1 minus alpha squared is like the residual value. So you take the residual value to be the same for the attention layer and the MLP layer. So now if you vary that, now if you fix sigma W to be around the optimal part, let's fix sigma W to be like 2.1, and then you look at how does it depend on the two residual values. Then you see a phase boundary like around here, roughly near the diagonal, and roughly when they are the same, but it's a nonlinear curve. And again, that's confirmed by numerics on the random embedding matrices, random QKW matrices. Okay, so, and then the same, you can draw the same plot, right? So you can study the gradient, and you see like the gradient being close to 0 in this plane is like another line here. So again, these two will overlap in this region, but then it stops. So there is a region like here, and then it stops working. So physically, I think what happened is this. So what happened is when you take steps that are small, then both are in control. And then when you go away, like if you take a too big a step every time, then one way or another, it becomes more chaotic. So basically, it's as we will see later, it seems like what happened is training doesn't really work very well there because like you're taking too big a step, so it's too chaotic. Any questions so far about the data? Okay, good. So then we want to verify that this permutation symmetry is a good approximation. So we take some ansatz where this is broken. So we basically you take the tokens and then group them into two groups, and then the inner product between one group and the other group is a different value, P2, and within each group is like P1, the diagonal is Q. So you can take such ansatz and then run the, then study how this evolves when you apply this, when you start with this ansatz and then you apply this transformer model for all the way until 36 layers. And then you see they gradually the ratio gets to 1, P1 over P2, start from some bigger value and gets to 1. So these different lines are for different layers. So you can imagine like start from the initial value somewhere 1.5, and then it just gradually go down. And then it goes down slower for smaller alpha because just the layers are closer to trivial. But you see this is confirming that it's okay to focus on that permutation invariant ansatz because it's kind of stable. It's stable in this way. And then beyond this, we studied some other kind of modifications just towards the more realistic model. So one thing is in the actual language model, there is this causality. Like you don't want the next token to depend on the future tokens. You only want to depend on the past token. So then you just mask out the attention to the future. And so every vector only depends on the past vectors. So we can do this, although, yeah, we can do this for this model. And then we can do the same calculation, like the two criteria, the token angle. How does the token angle depends on the transformer? How does the token angle evolve from input to output, and how does the gradient size evolve? Right? So you see, it's different. So the causality has a quite strong effect. Like this picture before looks like the critical value is like going up, and then now it's going down, or close to similar. And this one is qualitatively similar to before. So we don't really know what's the physical reason, like why it's going down here rather than going up. I don't have a good interpretation of that. So, but basically, you see, okay, so we can do the same kind of analysis, although we don't have this kind of permutation invariant ansatz and analytical control, but numerically you can use the same criteria to study what are the best initialization for other kind of more general models. And then okay, so that's the numerics on the initialization part. And then there is the we want to verify, because the intuition is that the initialization at the critical value helps with training. Right? So the intuition is that you want models to be close to these critical values. So you have these criteria for these Lyapunov exponents, and you want them to be close to 0. But then we want to directly verify that indeed these models close to the transition point works better. So what we did here is, for this very small model, Aditya trained this on this Shakespeare's plays, and then you get something which kind of not really Shakespearean, but kind of much better than the random tokens from the beginning. So then the thing to look at is so at least well, by the way, this is just to test the hyperparameter dependence. So the training actually wasn't done by tokens, it was actually by letters. So you see something like this. So yeah, so just letter by letter. So you see more English words did come out. But then so then the picture to look at is like, how does the test loss depends on the hyperparameters. So this is for different alpha. So if you choose a fixed alpha, then you choose different sigma. This is sigma W. Right? Sigma MLP is sigma W. So it's the width of the MLP layer. So when you train that, then the minimal test loss means like the optimal place where you should choose, right? You should initialize the model at the minimal test loss, and then you see the minimal test loss indeed lives in this yellow region, and then at some point here, it basically stopped working. Right? So the alpha, this is around 0.3. 0.3 is the red one. So basically, the model just stopped training when you go out this region. So it's hard to find the actual minimum. So that's what happened at this turning point. So like these minimum are probably not so useful because they are like almost flat here. Yeah, but so this part is more like the actual, like you see the minimum is going up a little bit. So we don't know why it's like this rather than like that. So, but it's consistent with the theory, but it's not like the theory doesn't immediately tell you it's this. So at least it's consistent. Yeah, so that's pretty much what I want to talk about. And so it's a simple kind of phase diagram, and we see that the theory agrees with different kind of testing. So the simple kind of averaging theory, like average the iteration equation, agrees with the more realistic calculations. So that seems to be a good way to guide the actual model. And by the way, I forgot to mention earlier, like why we were looking at tangent, parabolic tangent, because the intuition is you want some critical point, so you want some balance between something that make you converge and something that make you diverge, right? So you want some balance between the collapse and the exponential growth. And if you use like rel U, then it doesn't really change the angle of the vector, like because it's kind of linear. So although it could change the amplitude of the vectors, but the angle almost doesn't change. So that's one problem that we don't completely understand, because if we use rel U, we won't be able to find such fixed points. But of course, in practice, they are very good, and it's a useful function. So that's something that, I mean, maybe because we are not in reality, we're not in this deep limit, we are finite depths. So maybe that's one reason. So yeah, but there's an open question there. Like if you choose a general nonlinear function, then you can find this kind of critical point this way. But rel U doesn't seem to fit into this picture. And then okay, so so I think there are some interesting things we can think about based on this. So the one open question is like, I mean, what other than these two measures, are there other measures we want to find? Like, are there other measures that are relevant or maybe more relevant for what's a useful transformer? And then there is a question of if the only thing we care is are these nonlinear functions are doing this job of keeping you at the critical point, then there are many other functions that can do this, right? So can we just think about other functions other than attention? And then there is another question, which is this causality, which seems to be very important. Physically, it's very important for the predictability of the model, but we haven't taken into account of that in this discussion. So how do we have a better description and understanding of that? So I think these are the open questions, and I will end here. Thanks.
Thank you.
Questions? Maybe I missed this point, but when you talked about the iteration, you are not including the normalization and the residual part, or you are?
We're including it's the pre-norm. So we first do the normalization and then send it to the attention, and then before we send it to the MLP, there's another normalization. So there's no normalization after applying it.
And I guess for parameter, for choice of alpha, you could turn off the residual part.
If alpha equal to 1.
Yeah.
But we are always in the limit where alpha is close to 0. So you see so one thing this confirms, it probably was known before, but one thing that confirms is you want to stay in the small alpha region, because for the big alpha region, these two lines do not overlap with each other. So there is this critical line, and the other one start to bifurcate with each other. So that's one reason to stay with small alpha, smaller than 0.3.
So since you included the norm less, I'm curious if
the Mac stopped working. Sorry. Yeah,
that works.
Yeah.
Okay. Do you get any intuition for why having the norm just after breaking off the residual layers is more stable than what's called the post norm after?
That's an interesting question. Yeah, we certainly can study both cases. I don't know if the iteration equation difference tells you anything about the stability. Aditya, do you have any comment?
Yeah, I think I'm also confused about this point, and what's a bit strange is that at the average level, you can perform post-norm at initialization just by taking, alpha 1 and alpha 2, so that the sum of their squares is 1, or whatever. You can choose their sum of their squares. Yeah. So it's not clear why this post-norm would be different, at least at this average level. So I think that's maybe why we can't see that in our numerics or analytics, because of that.
So they are different. We can see the difference in the iteration equation, right? But maybe they don't change things qualitatively.
Well, let's
Okay,
thank
thanks.
Xiaoliang again.
I just leave.